Good morning, everyone. My name is Aditya Ojha, and today I'll be presenting on privacy preserving technologies. Uh, I'm from New York University, and my net ID is AO2612. Specifically, we'll be discussing three crucial privacy enhancing methods, which are federated learning, differential privacy, and homomorphic encryption. These technologies are essential in safeguarding sensitive information in an increasingly data driven world, and their applications span across industries like healthcare, finance, and mobile technology. I'll be walking you through the key aspects of these technologies, their system engineering breakdown, as well as their challenges and how they can shape the future of privacy in machine learning and data driven applications. Let's dive into the first part of the presentation with an introduction to what PPTs are and how they matter. Okay, so here's a quick overview of what we'll be covering today. Let's start with an introduction to privacy preserving technologies and a brief look at their history. Then we'll dive deeper into three main technologies, which are federated learning, differential privacy, and homomorphic encryption. After that, we'll explore the concept development stage, which includes need analysis, concept exploration, concept definition, and concept validation. We'll also look at how these technologies are applied in different sectors, the challenges they face, and the ethical, legal, societal implications involved. Finally, we'll wrap up with a conclusion summarizing the key points and future directions. Okay, moving ahead. To begin with, let's define privacy preserving technologies and why they are becoming increasingly critical. In today's digital world, personal data is constantly at risk, largely due to advancements in data driven applications, including artificial intelligence, machine learning, and big data analytics. Privacy preserving technologies or PPTs are designed to protect sensitive data, ensuring privacy while still allowing industries such as healthcare, finance, and retail to benefit from data driven insights. These technologies are essential for ensuring that we can leverage data responsibly. The core methods we'll focus on today are federated learning, which allows collaborative model training without centralizing data, differential privacy, which adds noise to the datasets to protect individual data, and homomorphic encryption, which allows computations on encrypted data without ever decrypting it. These approaches also help organizations comply with strict privacy regulations like the GDPR, which is General Data Protection Regulation, and the California Consumer Privacy Act (CCPA), which mandates stringent data privacy and security practices. Moving ahead, to better understand where the privacy preserving technologies are today, let's take a look back at how they evolved over time. The need for PPTs began to surface in the early 2000s as industries became increasingly reliant on data driven systems. With more personal and sensitive information being processed, the need to protect that data grew significantly. In 2006, a major breakthrough occurred when Cynthia Dore and her colleagues introduced differential privacy. This mathematical framework provided a way to protect individual data points by adding noise, marking a significant step forward in privacy preservation. Then in 2009, Craig Gentry introduced the concept of fully homomorphic encryption, which enabled computations on encrypted data. This was revolutionary because it allowed data to remain secure throughout its entire life cycle, even while being processed. Another key milestone came in 2016 when Google researchers developed federated learning. This method allows machine learning models to be trained across distributed services without centralizing data, making it a significant step towards decentralized privacy first models. The importance of privacy preserving technologies was further emphasized with the passage of the GDPR, the General Data Protection Regulation in 2018. The GDPR set strict data protection standards in Europe, driving industries to adopt privacy preserving methods to comply with the law. Similarly, in 2020, The California Consumer Privacy Act (CCPA) was enacted in the US, reinforcing the need for privacy protections at both legal and technological level. Over the years, these milestones have significantly shaped the development of privacy-preserving technologies, and they continue to evolve in response to both technological advancements and regulatory requirements. Now, let's dive deeper into the three primary preserving technologies that form the backbone of modern protection efforts. First is federated learning, or FL. Is a decentralized approach where machine learning models are trained across multiple devices without requiring raw data to be centralized. This method ensures that sensitive data stays local, significantly reducing risk of exposure. Next, we have differential privacy, which is a powerful technique that adds noise to the data, like control amounts of noise to the data, ensuring that individual data points remain private while still allowing meaningful analysis. This technique is particularly useful in situations where sensitive data sets like medical records are analyzed. Lastly, there's homomorphic encryption, a cryptographic method that enables computations to be performed directly on encrypted data. This is incredibly valuable because it ensures that data remains secure even during processing. But it comes with challenges, particularly in terms of computational overhead. Each of these technologies plays a distinct role in preserving privacy. While they all have their unique strengths, they also come with trade offs in terms of efficiency and complexity. Now, let's take a closer look at federated learning, one of the key technologies used in privacy preserving systems. This diagram provides a great visual representation of how the process works. As you can see, we have three separate organizations: Organization 1, Organization 2, and Organization 3, each with their own local model. These local models are trained on data that never leaves the organization's internal environment. This is crucial aspect because the raw data, whether it's personal, sensitive, or confidential, stays with the organization's control. In federated learning, these organizations don't send their data to a central server. Instead, they only send model weights or local updates to the federated server, represented at the top of the diagram. The server then aggregates these updates to create a global model. This global model benefits from the collective data of all the organizations without ever directly accessing the data itself. This approach has been particularly effective in privacy sensitive fields like healthcare and finance. For instance, in healthcare, hospitals or clinics can train models to detect diseases without sharing patient records. Similarly, financial institutions can collaborate on fraud detection models without exposing customer transactions. Moving ahead, now let's take a closer look at differential privacy, which is a method designed to protect individual privacy while still allowing useful data analysis. Differential privacy works by adding noise to the datasets. This noise ensures that the removal or addition of a single data point doesn't significantly affect the overall outcome. This protects individual records from being identified. This technique is commonly used in data analysis and machine learning, especially when working with sensitive datasets like medical records or financial transactions. It enables organizations to gain insights from the data without compromising user privacy. As you can see in the diagram on the right, the idea is that analyst queries a database, but the system adds noise so that the result is approximately the same whether or not a specific individual data is included. The two databases, database 1 and database 2, represent different query results, one with the individual data, one without. The crucial point is that the difference in outcomes is negligible, meaning it's nearly impossible to tell if a specific person's data was involved in generating the result. This mechanism makes it challenging for anyone analyzing the data to reverse engineer or for any personal details, even with access to multiple queries. In doing so, differential privacy strikes a balance between data utility and individual privacy, which is key for organizations that need to work with sensitive information. Moving ahead, next we'll discuss about homomorphic encryption. which is another powerful tool in the world of privacy preserving technologies. Homomorphic encryption allows computations to be performed directly on the encrypted data, meaning that at no point does the data need to be decrypted during processing. This is particularly important because it ensures that sensitive information remains secure even when it's being processed or analyzed. For example, in healthcare, you could run complex analysis on encrypted patient data without ever exposing the raw data itself, ensuring privacy at all stages. Homomorphic encryption has vast potential, especially in fields like finance and healthcare, where sensitive data needs to be protected, but secure data sharing and analysis are still essential for advancing outcomes. However, one of the biggest challenges associated with homomorphic encryption is its high computational cost. Processing encrypted data can be significantly slower and more resource intensive than working with unencrypted data. As a result, researchers are constantly looking for ways to make it more efficient for real world large scale applications. Moving ahead, we can see in the diagram that the whole compute encrypted data with homomorphic encryption diagram, in which we have a system and it encrypts, sends it to the other user, and the user can decrypt what the actual information was, and there can be no man in the middle attacks because the data is well encrypted. This can be used in various fields and yeah, mainly that. Moving ahead, let's talk about concept development and the different stages we have. So the first stage we have is need analysis, which is pretty self-explanatory. In this stage of concept development, we focus on need analysis for privacy preserving technologies. The primary objective is to identify the key system requirements and goals that will drive the creation of PPTs. First, it's important to define the target user groups. These include industries that handle sensitive data, such as healthcare, where protecting patient information is crucial, and finance, where securing customer transaction data is essential. Mobile technology is another major area with applications like personalized services requiring strict privacy measures. The next key challenge is balancing privacy and utility. We need to protect individual privacy without sacrificing the usefulness of data. For instance, in differential privacy or DP, adding too much noise can reduce the accuracy of the data. So we need to strike the right balance between privacy and maintaining the integrity of the information. Another critical factor is regulatory compliance. Technologies must comply with legal frameworks such as the General Data Protection Regulation (GDPR) in Europe or the California Consumer Privacy Act (CCPA) in the United States. These regulations ensure these regulations are designed to to protect individual data and impose strict guidelines on how organizations handle privacy. Finally, stakeholder management is essential. This includes collaboration between the end users, such as hospitals or financial institutions, the regulatory bodies that ensure compliance, and the organizations developing these privacy technologies. Engaging all the stakeholders help to ensure that the privacy preserving solutions are both effective and practical in real world scenarios. Moving ahead, we can go to the next stage. After identifying the key needs, whatever we wanted, the next stage in the development process is exploration, known as concept exploration, where different design methods are investigated to meet needs. The first focus is on technology integration. In privacy preserving technologies, combining methods like federated learning, homomorphic encryption, and differential privacy can create a comprehensive solution. Each of these technologies addresses a specific aspect of privacy. FL ensures that data stays local, HE allows secure computation on encrypted data, and DP protects individual privacy by adding noise. Next, it's important to explore new techniques. Emerging technologies like secure multi party computation, SMPC, and zero knowledge proofs like ZKP offer additional methods for preserving privacy without sharing sensitive information. These methods are still in their early stages but show great potential in enhancing security and privacy of systems. Finally, one of the biggest challenges during concept exploration is balancing trade offs. Privacy preserving methods often come with trade offs in terms of performance and utility. For example, while differential privacy provides strong privacy protections, it can also reduce the accuracy of machine learning models by introducing noise. Similarly, homomorphic encryption offers strong security but can also slow down computations due to its high computational cost. Finding the right balance between privacy and system performance is a critical part of this stage. Going ahead to the next stage, we have the concept definition stage, which is one of the other very crucial parts of concept development. After exploring the various design methods, the next stage is concept definition, where the best ideas are formalized and the system architecture is outlined. At this stage, we define the system architecture, which typically includes several layers. These layers could involve secure data storage, encryption modules, and distributed learning systems. It's important to design these components in a way that ensures they work together efficiently while still meeting the privacy goals. Once the architecture is defined, prototyping is used to validate that the systems work as intended. Prototypes help us evaluate whether the system meets performance indicators such as response time, accuracy, and scalability, all while ensuring that privacy protections are in place. Finally, we establish privacy metrics to evaluate how well the system preserves privacy. For example, in differential privacy, we use privacy budgets to control the amount of noise added. And in homomorphic encryption, we measure the computational efficiency to ensure the system can handle the required computations without necessary delays. At this point, the concept is well defined and the system can improve into further development and testing. Now, once the concept is defined, a prototype is built, the next part is to validate that whatever we have done up till now is actually working or not. And that makes sense. So, naturally, the next stage is the concept validation. Here, we rigorously test the system to ensure it meets its privacy and performance goals. At this stage, we begin by testing the system in real world use cases. For example, if the system is being used in healthcare, we would validate it with actual medical data sets to ensure that it protects patient without privacy, without compromising the usefulness of the data. Protects patient privacy without compromising use. Similarly, in financial industry, we would test the system with real transaction data to ensure secure and efficient processing. As a part of this validation process, we follow an iterative improvement cycle based on the feedback from testing. We define the system performances and privacy mechanisms, making sure adjustments as needed to address any shortcomings. Finally, one of the most important aspects of concept validation is ensuring that the system strikes the right balance between privacy, accuracy, and efficiency. A system that maximizes privacy but sacrifices too much accuracy or is inefficient in processing data may not be practical. Therefore, it's essential to find the right balance so that the privacy at every level, either it's for the patients, either it's for the users, is protected without significant trade offs in the system's effectiveness. Now, moving on to the next part of system engineering perspective, we'll have to talk about the engineering development stages and how it works. So, yeah. So, during the engineering development stage, the main goal is to create and use a shared learning system that protects privacy. Differential privacy, multi-party computation, and homomorphic encryptions are all built into the system to make sure privacy, scalability, and speed. The next part explains the system structure and how privacy is protected and how it can be made better. Moving to the next part, in system architecture design, um, just a second. Yeah. So in the system architecture design, the focus is on creating a modular and scalable structure that ensures data privacy while maintaining system performance. The architecture operates in two main components. On the client side, devices perform local model training using their private data to ensure privacy. Deep differential privacy is applied. Differential privacy is applied, which introduces Gaussian noise to the updates before they are sent to the server. This step ensures that the individual data points remain confidential and cannot be reverse engineered. On the server side, the system employs secure aggregation techniques which combine multi-party computation and homomorphic encryption. MPC ensures that multiple parties can collaborate on computations without revealing their individual inputs. At the same time, HE allows computations to be performed directly on encrypted data without the need of decryption. This dual layer security ensures that updates remain private throughout the process. The workflow follows the federated learning process where the server distributes the model and configuration to selected devices. Devices perform local training on the data, and encrypted model updates are sent back to the server for aggregation. The diagram shown illustrates that this workflow across two rounds capturing key stages such as device selection, configuration, training, reporting, and aggregation. It also highlights real world challenges like device rejections due to failures or insufficient resources. Ultimately, this design ensures scalability, privacy, and efficiency, enabling large scale deployments without compromising data security or performance. Going to the next stage, we can start talking about the implementation of privacy mechanisms. In the implementation of privacy mechanisms, three key techniques ensure data privacy at every step of the federated learning process. First, differential privacy introduces Gaussian noise to local model updates on the client side before they are shared with the server. This prevents individual data points from being exposed. Second, on the server side, secure aggregation combines local DP with multi party computation, MPC. MPC allows the server to aggregate encrypted updates without ever accessing the raw data. Finally, homomorphic encryption (HE) is implemented to perform computations on encrypted data updates. This ensures that even during processing, data remains encrypted, providing an additional layer of security. Together, these mechanisms form a robust privacy preserving pipeline. In the optimization for scalability and convergence, we address key challenges related to resource constraints, communication overhead, and convergence performance. First, client selection techniques are used to randomly select clients while considering their resource availability, such as bandwidth and battery life. This reduces network overload and ensures effective participation. Second, communication optimization methods like gradient sparsification and compression minimizes the minimizes the size of updates sent from clients to the server. This significantly reduces bandwidth usage, improving efficiency at large scale systems. Finally, we carefully manage the convergence trade-offs. While differential privacy adds noise to protect privacy, this can reach to model accuracy. To balance this, we increase client participation or the number of training routes to ensure that the model converges effectively without compromising privacy. In the experimental validation results, we evaluated the system using benchmarks datasets like MNIST and CFIR10 to measure performance under privacy constraints. The results demonstrated that the hybrid one approach, which combines differential privacy with multi party computation, achieved an accuracy improvement of 5 to 10% compared to traditional methods. We also observed that the negative impact of DP noise on model accuracy could be mitigated by increasing the number of participating clients, improving convergence rates. Additionally, communication optimization techniques such as gradient falsification significantly reduce bandwidth usage by up to 40%, ensuring the system scalability for large scale deployments. Moving ahead, let's talk about the next stage. In the post development stage, we focus on ensuring the system remains efficient and robust after deployment. First, monitoring performance involves real time tracking of critical metrics such as model accuracy, convergence rates, and resource usage. This helps identify bottlenecks and areas of improvement. Second, we implement feedback based improvements where the system dynamically adjusts parameters like differential privacy noise levels or optimizes client selection strategies to maintain accuracy and privacy. Lastly, to ensure communication efficiency, techniques like compression and pacing methods are applied. These strategies reduce bandwidth consumption and enable the system to scale effectively across thousands of devices. This stage ensures that the federated learning system is adaptable, efficient, and capable of handling real world operational challenges. Moving ahead, now that we have covered the core privacy preserving technologies, let's look at how these technologies are applied in real world scenarios across different industries. In healthcare, privacy preserving technology like federated learning allow hospitals and medical institutions to collaborate on disease detection models without ever sharing raw patient data. This ensures that patient privacy is maintained while benefiting from advances like medical research and diagnostics. It also helps hospitals to comply with strict regulatory regulations like HIP. In the finance sector, homomorphic encryption plays a crucial role. For example, financial institutions can perform fraud detection or, or secure data transaction processing without exposing sensitive customer data. This particularly imp- this is particularly important as the finance industry handles highly sensitive information on a daily basis. On mobile devices, differential DP is commonly used to ensure user privacy and personalized services like predictive text or targeted suggestions. By adding noise to the user data, companies can offer personalized experiences while still protecting privacy. In smart cities and IoT, where there are vast amounts of data being processed in real time, PPTs ensure that personal data remains secure, and IoT devices are often used for traffic management, energy consumption tracking, and more. PPTs make sure that while data is processed, the privacy of individuals contributing to the data remains intact. Let's look at the system engineering challenges. We address the real world constraints and issues that arise during deployment of PPTs, federated learning systems. First, device availability is inconsistent due to factors like limited battery, intermittent network connectivity, and hardware availability, which can disrupt participation during training rounds. Second, communication bottlenecks occur because frequent model updates between clients and the server consume significant bandwidth, especially in large scale systems. Third, the heterogeneity of devices poses challenges as devices with varying computational resources contribute unevenly to the training process, slowing down convergence. Additionally, the privacy utility trade off remains critical. While DP ensures strong privacy guarantees, it reduces model accuracy by adding noise. This requires careful optimization. Finally, security threats, such as model inversion and membership inference attacks, highlight the need of robust multi layered privacy mechanisms to prevent adversarial data extraction. Overcoming these challenges is key to making privacy preserving technologies scalable, secure, and effective in real world applications. Now let's look at the ethical, legal, and societal implications. One major concern is fairness and bias, even with PPTs like FL or DP. ML models can still inherit biases present in original data. This can lead to unfair outcomes, particularly when the data is biased towards specific groups. It is important to ensure privacy measures do not exacerbate existing biases. Another issue is transparency and consent. Users must be informed about how their data is being used and protected, especially when complex cryptographic methods like HE are involved. Then there's the question of data ownership, like who truly owns the data? Is it the like who truly controls the data that has been anonymized or aggregated? In many cases, organizations claim ownership, but individuals may not have control over how their anonymized data is being used in these models. From a legal perspective, compliance with global privacy regulations like GDPR and CCPA is becoming more complex because they are creating more stringent rules, which in turn is leading to companies ensuring that privacy preserving technologies meet legal requirements can be challenging because, especially for organizations operating across multiple jurisdictions. Finally, there's a societal impact to consider. If not implemented responsibly, PPTs could disproportionately affect marginalized groups, potentially deepening inequalities. In addressing these in addressing these ethical, legal, and societal issues, it's critical to strike a balance between technological innovation and broader implications for society. In the recommendation sections, we focus on steps to advance the adoption and effectiveness of privacy preserving technologies. First, it's essential to invest in advanced research areas such as post quantum cryptography, SMPC, and effective HE to address challenges like computational overhead and security. Second, we must enhance communication efficiency by developing improved gradient compression and bandwidth optimization techniques to scale federated learning systems effectively. Third, generating ethical guidelines is critical to ensure fairness and transparency. And fostering collaboration amongst researchers, policymakers, and industries will drive innovation and accelerate the adoption of these technologies. Lastly, raising public awareness about the benefits and societal impacts of PPTs will build trust, encourage adoption, and support a privacy conscious digital future. To conclude, PPTs are becoming increasingly essential in a world that's driven by data. They allow us to protect sensitive information while still extracting valuable insights from data for decision making. The core technologies, FLDP and HE, are at the forefront of this movement, each of these helping in different kinds of ways. However, as we have discussed, they still all have significant challenges that they face. And looking ahead, emerging technologies like SMPC and post quantum cryptography offer exciting opportunities for overcoming some of these limitations. And lastly, it's important to remember that the success of these technologies also depends on addressing the legal concerns. As we move forward, balancing privacy, fairness, and transparency will be the key to ensuring these technologies serve the public good. Thank you all for your attention throughout the presentation. I hope this session gave you a deeper understanding of privacy preserving technologies and their importance in safeguarding sensitive data in today's digital world. My name is Aditya Ojha, and my net ID is A02612, and this is me signing off. Thank you so much.